So the self-attention mechanism that we have just learned has played a huge role in the design of transformers. And transformers, I would say, it is kind of now the state of the art of many neural networks in many domains. So the idea of these transformers is the following. So we will have a an input, so we have some inputs, some outputs, they are sequences, so they will the sequence that we just saw, each one of the tokens will be embedded, and they will be added or concatenated depending on the application, the positional encoding that we will learn now what it is. Then this vector goes through an encoder, and this encoder has to, for instance, well, it has these multiple head attentions, and then add a normalization, and there is a skip connection here, and then there is a neural network, feed-forward neural network, and then add a normalization, and then this goes into the multi-head attention of the decoder. The decoder has kind of the same structure with a masked multi-head attention, so it cannot look into the future. Then multi-head attention, and then feed-forward neural network, add normalization. There are a number of skip connections, and then it goes through a linear layer, softmax, and it is producing some output probabilities. There is a shifted right of the output, and the problem is that so this shift right is made so that at the time t the network can only use the data from time t minus 1, so there is a shift by this start of sequence. So x0 can predict start of sequence, and then y1 can only use x0, and y2 can only use x0 and x1, and so on. So nothing that we don't know already except the positional encoding. The positional encoding, yeah, there is some comment here. So we see that this block of multi-head attention, add and normalization, feed-forward, add and normalization is somehow repeated in the encoder and the decoder. So here, this part is doing a communication between all tokens in the sentence, in the sequence, and we have already seen through this attention mechanism how that happens. And then this part of the network is doing a computation. So now this one knows all the attentions, and it knows because it comes from here. It comes the embedding of each one of the tokens in the sequence. So with these embeddings and the attentions, then it uses a dense neural network to produce the output. So this is just a computation for each one of the inputs, for each one of the tokens, what should be the output. Okay, good. So what is positional encoding? So without positional encoding, all the words would be treated in the sentence without knowing whether that word appears at the beginning or at the end of the sentence. So what we want is to give an order to all those words. So to know that which word was first, which word is second, and so on. So we do that through the positional encoding. So we have word number 0, word number 1, word number 2, and for each one of these words we will associate a vector. This vector has the same size, not necessarily, but has if you fix the total number of words that you can accept, so you fix it to 10,000, then you can do this thing. So it pos is the uh, position, and so the current position, position 0, position 1, position 2, and I will be the coordinate with in the vector, in the output vector. So for a given position, the even coordinates are calculated this way, the odd coordinates are calculated this way. So at the end, what you do is you associate to each position, you associate the vector. So this vector is 1, 0, 1, 0. The second word is associated with the vector 0.8, 0.6, 0.6, 0.8. Always the same vector, always. So this does not depend on the word itself, but on the position of that word. So it depends on the original transformer. This positional encoding vector was added to the input embedding. Now there are variants in which you can concatenate, or you can put even a network if you want. You can put a neural network that takes the positional encoding, this input embedding, and produces something else. So these vectors look like this. So this is the position index, so word 0, 1, and so on, and then how they what are their values depending on the embedding dimension. So if you embed into vectors of size 512, so these would be the values. So they go from -1 to 1 because they're coming from sine and cosine functions, and all these small lines that we see here are oscillations. And so what we see is that every word gets a different encoding, so positional encoding. Okay, now these generative general purpose transformers. So this GPT is general purpose transformers. So what we have is an input. It goes so an input word. It goes through the embedding. Then we add or concatenate the positional encoding. Then there is a layer of dropout, and then there is a block. So the structure of this block is a layer normalization that we have already seen, multi-head attention module, dropout, skip connection, and then layer normalization, fully connected network, dropout, skip connection, and this is the block, and then you have many blocks of this kind, and then a layer normalization, fully connected, softmax, and this is your output. So what about when we process images? So we process images, we can apply these vision transformers. That the idea is the same. So instead of tokens, now what we have are patches in the image. So you take each one of the patches, you go through an embedding of those patches, and here they chose to do a linear projection of the flattened patches. So this is a matrix that you have to learn. Then the patch and positional embeddings, they are concatenated, so they are not added. Here in this paper, in other papers they may do something else. And then they go through a transformer encoder. So we have this encoding here. So we go only through the encoder, and then you have a multi-layer perceptron, so a feed-forward network dense, and then you predict. And what is interesting to see is that the first convolutional layers of some, for instance, AlexNet was a convolutional neural network, and it was not a transformer. But the first convolution filters, they look like this, and in this Bayesian transformer, the first linear embedding filters, so these ones here, they also look kind of the same kind of stuff. You have also swing transformers. So swing transformers, so the visual transformer that we just described is making patches of the same size, and in these swing transformers, the size of the patches are smaller and smaller. So that gives a hierarchy of what are the details, what is the context of that patch in the full image, and also they are shifted. So not all of them. So somehow they are shifted so that there is an overlapping between patches. So here the patches, they are much more, they're all aligned, and then there might be some boundary effects between patches. Another relatively famous architecture that came out related to transformers is this Mamba. Mamba is based on these state space models whose ingredients somehow remind like the recurrent networks we already studied. So they will have an internal hidden state, and this hidden state is updated from two sources. One is the hidden state itself, and then the input. So this input is so this matrix B is kind of learning matrix, and A can be thought as a forgetting matrix, and then this D, so the output is made by the hidden state and the input. So somehow this matrix D is a kind of a skip connection. So these are the formulas for the regular state space model, and this state space model participates in this way. So what it does is you have an input, and then you have two linear projections. Linear projections are very cheap to compute and to propagate the back projection, the gradient. Then you have a convolution, and then you have nonlinear functions. These somehow communication step. So we divided before self-attention into communication plus computation. So now the multi-head attention we have substituted by this SSM, and then another linear projection. So in general, very cheap operations, and this Mamba has somehow been very fast. So here you have so it is almost as fast as the recurrent neural networks that were extremely simple, but they have an effectivity that is an effectiveness that is somehow closer to the ones of transformers. The problem with transformers is that they are very expensive to compute, so the efficiency is very low. And as practice, we will play a little bit with these visual transformers. Now, somehow related architectures. So let us define this mixture of experts. So a mixture of experts is this architecture in which you have an input. This input, you will have an skip connection here, and then it will go through a gate. So this gate, you have a number of feed-forward networks that each one of them is considered to be an expert. So an expert that, given this input, it produces an output. So each one of the experts is receiving the same input. But then this gate is calculating what is the importance of each one of the experts for this particular input. So let's say that it produces this output, and then the outputs of each one of the experts will be multiplied by the importance of that expert for that input, and then all the outputs combined. And then you have the skip connection, add and normalize, and then you progress to the next one. So this is the standard dense mixture of experts. You may have a sparse mixture of experts in which you remove those connections or those weights that are not important enough. So let's say you take the top two, for instance. This could be another way. When you use this mixture of experts, you may want to add these load balancing laws. So that the load balancing laws somehow penalizes the gate of giving all the inputs to the same expert. So at the end, you are training one expert, but the other experts don't get any information, any training. So the mixture of experts transformer, what it does is it has in this block where we have self-attention, add normalize, and then the feed-forward neural network, so the dense neural network. So now instead of having a standard dense network, we will have this switching feed-forward neural networks. So that means that we will have here, we will have the routers, and so these gatings that we saw before, and they will, for instance, let's say that you allow only for the best. So if you allow only for the best, this one will go through here, through this weight. And you can have a mixture of heads. So for instance, here you can also have multiple heads that we have already seen, but we can have this router, so the gating that goes all the heads see all the out, all the input, but then each one of them is given a different weight. So yeah, and if you are more interested in this kind of architectures, we have here a number of links that I find them useful. If I all the links that also appear here, those are the ones that I have normally used to take the pictures, and if I leave them there, normally it is because the explanation around the picture is also very good. So let's stop here.